All right, we're studying this problem here. Maximize 2x plus 5y subject to these constraints in Excel. So we'll start off by making our model in the spreadsheet. So I like to put my decision variables up top. I've got x and y are their names, and I'll start them off with initial values 0. My function to maximize in this case is 2x plus 5y. The constraints, we've got a less than constraint that is 1x plus 2y is the left-hand side of it. We're going to evaluate ourselves. We're going to compare that to the right-hand side and make sure it's always less than. The right-hand side needs to be 16. The left-hand side, let's see, the next constraint is a less than constraint. 5x plus 3y, whatever we evaluate has to be less than or equal to 45. And then finally, we have an x and y are both greater than or equal to 0. These otherwise are unconstrained, so I'm going to let Excel Solver take care of that for me. We'll see how we can set the option. So if we want to find the objective function, then we would need to take the sum product of these values and these values. And same thing, since I've locked this cell, I can go ahead and drag this through and we can evaluate the left-hand side of the constraints. So for instance, when x is 1, then yeah, the objective function is 2. The first constraint is 1. That needs to be less than or equal to 16. And this also has to be less than or equal to 45. That's fine, but it looks like we could increase some of these values a little bit. We can get higher values of the objective function while still satisfying these are less than these. So I'm going to let Excel take care of that for me by going into Data and Solver. So what is the objective function cell? We want to maximize that. So we maximize it subject to by changing these cells, x and y variables, and we have constraints that these cells here need to stay less than or equal to these cells here. So we say OK. And make unconstrained variables non-negative. That's going to take care of our x and y are greater than or equal to 0 because I haven't put constraints directly on x and y. X and y, these cells are not involved in these constraints. These constraints here involve cells D4 through D5, so D4 and D5. I put them on these cells. I didn't put any constraints on these cells directly, and so they are unconstrained, and it will make sure they are non-negative for me. Simplex LP is the algorithm of choice because the problem is linear. I say solve. And Solver found a solution. We're going to keep the solution. Let's see, 0, 8 apparently was the solution. I'm going to go ahead and generate all three reports here, the answer report, sensitivity report, and the limits report, so we can see what they mean. And we're going to investigate those. First of all, let's before we look at those reports, so that generated these different reports, answer report 2, sensitivity report 2, and limits reports 2. Here's my spreadsheet model, it puts them before there. So before we continue and look at those reports, we want to look at the problem graphically. I've already set up the problem in Desmos.com's graphing calculator, and we can see this is not the optimal value of the objective function. It is up at 40. Here we go. Our solution is 0, 8 as we saw before. So this is the graphical solution. And so when we do the sensitivity analysis, we're going to compare it to the graphical solution and see what we can learn about it. So actually, let's go ahead and move this over. We can replace the problem for now. And let's take a look at each of the different reports that were generated. So answer report, what do we have here? The solution time, etc., a bunch of information about the problem. The objective cell, the original value was 0. That's what I had in the spreadsheet before anything, before I click solve in the solver, and then it optimized it to a value of 40. The objective function cell is cell D3. I guess we can confirm that. D3 is our objective function cell, yep. All right, what else can we learn here? Variable cells, decision variable cells. Decision variable x and y, their original values were 0 before I did anything. Their final values were 0 and 8. That's where I'm getting my optimal solution. Are they integer constrained? No, they're not constrained to be integers, but they're continuous variables. But it turns out that there was an integer solution. That happens sometimes if the constraints are intersecting at points with integer coordinates. But these were not supposed to be integer constrained. I didn't set up any integer constraints on those decision variables. Additional constraints, information about them. We have D4 is less than or equal to the left-hand side. D5 is less than or equal to the left-hand side. What were these? D4 and D5. Okay, so this constraint here, you can see that the left-hand side, 0 times 1 plus 8 times 2 equals 16. That's the left-hand side. It is satisfied with it. The less than or equal to constraint between the left-hand side and the right-hand side is satisfied with an equality constraint. That means that the constraint is binding. It is affecting our optimal solution. We can see that here, that constraint in our model. This was the red constraint, and this is the blue constraint. So this red one here, right? Our optimal point lies right on the line that defines the constraint. We don't have any slack, which we'll get to in a second. It lies right on that constraint. That constraint is binding. Whereas this constraint here, the blue one here, 24 is strictly less than 45. It's not equality constrained. There is distance between our optimal point and this line defining the constraint. So it is not binding. It doesn't affect our optimal solution. If we change this constraint, in fact, if we remove it from the problem entirely, that doesn't affect, this one, sorry, if we change this constraint, we can remove it from the problem entirely, and it's not going to affect our optimal solution. Our optimal solution is still there. Whereas the one that's binding, if we change that a little bit, it is limiting where our objective function value is, or what our optimal value of the objective function. If it weren't around, if that constraint weren't there, then we would be able to make the value of the objective function higher, right? If I delete this constraint, if it's not there, then I would be able to make this not just 40, I could raise it to 50, I could raise it to 60. It's binding, it's limiting us in how far we can maximize our objective function value. Okay, now the slack values, which we discussed just a second ago, if the constraint is binding, it has 0 slack. That means we cannot change either the right-hand side or the left-hand side. We can't change this value any without changing the optimal solution. If we added 1 to this, then we would have to move the optimal solution. It looks like we could get up to 41, maybe 42 or something like that. That changes the optimal solution. So if we, however, the slack value of constraint blue, the blue constraint, it's not binding, this blue constraint here. This is telling us that we can add or subtract 21. Let's see, if we subtract 21 from this, okay, so we can add 21 to the left-hand side, subtract 21 from the right-hand side. If we add 20 to it, no problem, the optimal solution doesn't change. If we add 21 to it, however, then this constraint also would become active. It would be satisfied by inequality. And if we added any more than that, well, the optimal solution is now going to be here. It's going to have changed. Okay, so a slack of 21 on that blue. That's quantifying how far away it is from affecting the solution to our problem. Sensitivity report. Let's take a look at this one. Decision variables x. The final value was 0 and the final value of decision variable y is 8. Well, we already knew that. Reduce costs on these. The reduced cost is like the shadow price on the, well, let's get to that in a second. We'll get to that after we talk about the shadow prices. Objective coefficient is 2 and 5. Well, we already knew that. That's just 2 and 5. That's part of the problem setup. Allowable increase is 0.5. Allowable decrease 1 times 10 to the negative 30. Okay, that means how much could we change the objective coefficient, and the point that we have, 0.8, will remain our optimal solution. Okay, let's go ahead and change this. We'll change the objective function coefficient. We're going to add, it says that we can add up to 0.5 to that. So add plus 0.1. plus 0.2, plus 0.3, plus 0.4, plus 0.5. At this point, we've added so much to it that we are beginning to change. We're just on the cusp. Look what happened to our optimal objective function line, the objective function line. It was not parallel to this red constraint before. As soon as we add 2 plus 0.5 to it, it becomes parallel. And look, if we add 2.6, 2.9, this is no longer the optimal point. We're going to be able to increase the objective function value further. Let's go ahead and see. If I make this 3, so add more than 0.5 to it, then it looks like I can get up to 42, 43 or something, a higher value of the objective function. It changes our optimal solution. But within the limits, allowable increase of 0.5, we can stray from the original 2 by 0.5, and we will still have 0.8 being an optimal solution. Okay, it says allowable decrease. Allowable decrease. So how much can we subtract from it? We can subtract 1, we could subtract 2, we could subtract 100, and we would still have 0.8 be the optimal value of the objective function. And we can't go any further. This 1e30, that means 1 times 10 to the 30th power. 10 to the 30th power, or 1 followed by 30 zeros. That's a really big number, and it effectively means infinity in Excel. All right, let's take a look at the next one. Decision variables y. Objective coefficient is 5, but how much can we increase it? It turns out we can increase that as much as we please, and we're going to still end up with this being the optimal point. Now, 0.8 is still going to be the optimal point, but we might have a different value of the objective function. Before, when we were modifying the first coefficient, it turns out that the value of x was 0 at the optimal solution. So we had the same objective function value regardless of how we changed this coefficient. This coefficient, 0.8, is still the optimal solution point, but we have a different value of the objective function. It's going to be 105 times 8 now, it looks like. So let's see, 105 times 8. Yeah, so we get up to here. So this allowable increase and decrease is the amount you can increase or decrease the objective function coefficient corresponding with a variable without change in the optimal solution point. You might change the optimal value of the objective function, however. So it says that we can decrease it by only 1. 5 minus 1, let's see what happens. This was at 40, right? So if it was at, we're here, and then we subtract minus 0.1, that's no, well, we have to change the value of the objective function, perhaps. Okay, so maybe this is now at 39 or something like that. But we change this to 5 minus 1, it says. Well, look, our line has now become parallel to this line again. And so this is not the optimal value of the objective function anymore, 31, 32, something like that. But look, if we change this 5 minus 2, our optimal value of the objective function is going to change. We can't make it there anymore. Let's say 30, nope, 20, 25, 26, 27. It's changed. We've changed to a different solution point. We've changed from 0.8 being our solution to 6.5 being our solution again. So how much, basically, this allowable increase and allowable decrease is how much can you change the values of these coefficients until the objective function is parallel to one of the constraints. And that is going to, initially, if you're right on the cusp, you're going to have lots of different optimal solutions. So in this case, you can choose anything along this line here because the objective function is parallel to one of your constraints. Any point on this line will give you the same optimal value of the objective function. But if you go over that just a little bit, then our original solution point 0.8 is no longer going to be an optimal point. All right, let's calculate the shadow prices. Let's bring this back to our solution. So the final value of these constraints is shown, yep, 16 and 24. or the final left-hand side values of the constraints. The shadow prices, that says, okay, this was the red constraint. How much, when I add 1 to the right-hand side of the constraint, how much does the objective function value change? Apparently it changes by plus 2.5. That's the new optimal value of the objective function. If we change by, that's for every unit increase. So if I change by 10, then I'm going to get 10 times 2.5 more in the objective function. That's valid only for a certain range. If I change by 14, okay, that's fine. Then we're still at 14 times 2.5. But if we change any more than 14, if we go up past this allowable increase, look, the vertex that is going to be the optimal point changes. Our optimal value of the objective function is no longer satisfied, but we can't figure out the change by the linear relationship, whatever we added to the constraint multiplied by the shadow price 2.5. This shadow price is no longer valid. This is actually the optimal solution point. We cannot add this amount. We can still only add, I guess, 14 times 2.5 times the optimal value to the optimal value of the objective function. And the allowable decrease, same sort of idea. We can decrease it by 1, and so we can subtract 1 from it. All right, then we can subtract 1 times 2.5, and well, that'll give us the new value of the objective function. We can do all the way up to 16 minus 16. And look, well, this is still going to be true. The optimal value is 0 now. 16 times 2.5 is 0. 40 is 40. 40 minus 40 is 0. There's only 1 point left. But if we take any more out of that, 16 minus 7 is greater than or equal to negative 7, or sorry, less than or equal to negative 7, because we flip the sign here just for visualization purposes, then our problem becomes infeasible. There's no feasible region anymore. We can't solve it. So the shadow price would no longer be valid. And same sort of idea here. The shadow price is 0 for this constraint, right? Well, that's intuitive, actually. How much does changing the right-hand side of this constraint change the optimal value of the objective function? 0. It's not active. It's not binding. It's not affecting the optimal solution at all. So we can change it by up to, well, we can add as much as we please to it. That's just going to bring it further away. We can subtract up to 21 from it. And you can see that that would start becoming the active or binding constraint if we change that, decrease it further. Then our shadow price of 0 is no longer going to be valid. It's going to start affecting our solution. And so let's get back to reduced cost. This says the reduced cost on decision variable x is negative 0.5. That's basically the same as the shadow price on the non-negativity constraints. We calculated the shadow prices on the red and the blue constraints. Now the shadow price on the green constraint is the shadow price on the non-negativity constraint on the x variable. That's the same as the reduced cost. So let's see that. If I add 1 to this, then I'm going to reduce my cost by 0.5. Right? If I change this to plus 2, well, it's a linear relationship, minus 0.5 times 2. That's the new optimal value of the objective function. And it turns out that there's a tight relationship, and you're always going to see this. There's a relationship between the reduced cost and the allowable increase in the objective function coefficient. It turns out that when you have a non-negative reduced cost, then these are going to be equal in magnitude. Now the reduced cost on y, the y is greater than or equal to 0 constraint, the non-negativity constraint on y, that is 0. Why? Well, this constraint isn't active. There is no shadow price on it, so the reduced cost is 0. And finally, we get to the limits report. Tells us the optimal value of the objective function, 40. We already knew that. The values of the decision variables yet again. So then we get to the lower limit and the upper limit. And these are the lower and upper limits on what you can change the decision variable value to and still satisfy the constraints. So this is saying that the lower limit on our x value that will still satisfy the constraints is 0. We cannot decrease it by any from our original place, 0. We can subtract nothing from it before we start violating a constraint. We can add nothing to it. We cannot go any higher than 0 without violating a constraint. On the other hand, for our y value, it's at a value of 8. We can bring it all the way down. We can go all the way down 0.6. That doesn't violate any constraints. 0.4, that doesn't violate any constraints. We can bring it all the way down to a lower value of 0 and still not violate any constraints. And so this is useful. If you don't like the optimal solution that you get for some reason, this will tell you at a glance that you can adjust the decision variables a little bit without beginning to violate any of the constraints.